Welcome to my video on circuit analysis. I'm going to do an example problem. So the example we want to look at here is we've got a 12 volt power supply here, and then we've got three resistors. R1 is a 2 ohm, R2 is a 6 ohm, and then R3 is a 3 ohm. And you'll notice that R3 and R2, the 6 ohm and 3 ohm, are in parallel. And that becomes in series with R1. So we're going to use that to our advantage to figure out some stuff. So part A is find the equivalent resistance for the circuit. Step 1, in the process of figuring out the equivalent resistance, we want to combine the 3 ohm and the 6 ohm in parallel. We're going to kind of break this circuit down and kind of turn it into something a little simpler. So now the resistance of 2 and 3, R2 and 3, is R2, R3, and we've got a video on this that talks about combining resistors in parallel. And so we've got 6 times 3 over 6 plus 3, which is just equal to 18 over 9, which is equal to 2 ohms. So there's a parallel combination of those two resistors. Now step 2, what we want to do is we want to combine R1 and this R23 we just calculated, because they are in series. So when we know the equivalent resistance now, if we combine these, so we've got R1 plus R23 will be the total equivalent resistance. So we know R1 is a 2 ohm resistor, and we know the equivalent combination of in parallel of 2 and 3 is 2 ohms also, so we know we've got 4 ohms. That's going to be our equivalent resistance. So now our circuit is going to essentially look like, if we want to do the equivalent circuit, we've got the 12 volt power supply again. That hasn't changed. And then we've got one resistor now, R equivalent. And that we know is 4 ohms. So we found the equivalent resistance of the circuit. Part B, determine the power requirements of the 12 volt power supply. Okay, so we need to know how much power this is going to have to deliver, because we've got to get the proper power supply. If we're going to order a power supply to build this circuit, we have to have the correct one. So the power on the supply, we know that's V squared divided by R equivalent. That's just the power relationship if we know the voltage and the resistance. The voltage is 12 volts. We square that. We know our equivalent resistance is 4 ohms. So that's 144 divided by 4, which is 36 watts. So that's the power of the power supply must be able to deliver to that equivalent load. So that gives us some information about what kind of power supply we need to have available. Part C, determine the power requirements of each of the resistors. So let's start with the one that seems the simplest to look at, and that's the 2 ohm resistor, which is the R1. And we know the current is going to be equal to the voltage divided by the equivalent resistance. We just calculated R equivalent. So it's 12 volts divided by 4 ohms is equal to 3 amps. Now, we know one of the power relationship is I squared R, and we know the current, and we know the resistance. So we'll just use that relationship. So we got 3 amps, quantity squared. The resistance was 2 ohms. So that's 9 times 3, that's 18 watts. So that one was a little simpler because we knew some of the basic information going in. Now for the 3 ohm and the 6 ohm resistor, we're going to have to take a little different approach. First of all, we need to think about what circuit we've got here. We've got the 12 volts, and then we've got essentially 2 resistors. we've got the 2 ohm coming in, and then this 2 ohm right here, that's going to be the parallel combination of the R2 and R3. So that's going to be the parallel combination of the 3 and 6 ohm, 3 ohm, parallel with 6 ohm. We found that in part A, so we know that. So now to calculate the power requirements of these two resistors in parallel, the 3 and the 6 ohm, we need to know the voltage across the 3 in parallel with the 6 ohm. Now we're going to use what's called the voltage divider, and I have a video on that. And so what we want to do is we will need to find this voltage V3 in parallel with 6. What's the voltage across that? Now our voltage divider formula tells us that that's going to be equal to 12 volts. And we take into account the resistor it's dropping across, so it's the 2 ohm right there, the bottom one, divided by 2 ohm plus 2 ohm. That's going to be 24 divided by 4 is going to be 6 volts. So we know there's 6 volts across this parallel combination of the 3 ohm and the 6 ohm. So now what we've got, and continue to determine the power requirements, we want to think about this. The circuit breaks down to, we've got there's the 6 volts going to ground or completing the circuit. There's our 6 ohm and 3 ohm. So now it becomes a little more straightforward to calculate the power requirements for each of these resistors. We know the voltage, we know the resistance, so we can use the power relationship. That's going to be for the 6 ohm. When we know the voltage and the resistance is V squared over R. So that's 6 squared because there's 6 volts across it. And we have the resistance of 6 ohms. So that's just going to be 6 watts. So that is the power requirement of the 6 ohm resistor. Now if we want to go look at the 3 ohm resistor, the power requirement for the 3 ohm resistor, once again V squared over R, because we know the voltage and we know the resistance, 6 squared, because that's the voltage. Now the resistance is 3 ohms in this case, so it's going to be 12 watts. 6 squared is 36, divided by 3 is 12. Okay, so now let's do a little double checking on this whole thing. What we want to do is we're going to check and make sure the power of the supply is equal to the power of the load, because that energy has to go somewhere. And we have to make sure that they're the same. When we know the power coming into the supply or delivered by the supply was 36 watts, we calculated that. Now we've got the 3 resistors where the load is dissipated, the power is absorbed, mostly converted into heat. 3 ohm plus the power, we've got these 3 resistors. And we calculated already that that was 18 watts plus 12 watts plus 6 watts. Now that's 18 plus 12 is 30 plus 6 is 36 watts. So this agrees with that. So that's a good check of all of our math and our problem, because the power in is equal to power out. Energy is conserved. All right, well, thank you for watching this video. Hope you got something out of it. And if you did, like and subscribe to my channel.